Okay, hi, I'm back. I'm going to make a video now about magnetism. There's two bits to magnetism. First one is when things move in a magnetic field, which is the basis of motors. The second thing is when we use magnetism and magnetic fields to create electricity. And I think this second bit, the creating electricity or electromagnetic induction, induced potential, the generator effect, all what it's called, is the trickiest bit. So I'm making a video on this. Now, this video is a bit different. I am going to start talking about the GCSE stuff, then I'm going to move on to the A-level stuff. So, I mean, I recommend if you're doing A-level, you watch the whole thing. Whereas if you're doing GCSE, watch the first bit and then, just switch off for the second bit, because you don't really need to know what's going on with the A-level unless you're interested. I think that I am not going to do like edits and cuts, and I probably blather a bit. So feel free to watch it at 2 times the speed. Also, the bin men are here, so there's a lot of background noise. So sorry about that in advance. Just 2 times speed and you should be fine. So, for the GCSE, the main bit we need to know is that when an electrical conductor, so this bit here, when an electrical conductor moves relative to a magnetic field, we induce a potential difference. Now, this idea of the electric conductor moving relative to the magnetic field, often we instead of saying this large word, it's all about the idea that it could be either the magnetic field moving, could be the electrical conductor moving. We can move the magnetic field by creating a magnetic field, taking one away, or just physically moving them. We often say cuts field lines. Right? So instead of this bit here, moves relative, when an electrical conductor cuts field lines, and that's fine. At A-level, it builds in the idea that this is actually called magnetic flux or flux linkage, but at GCSE, they always allow cuts field lines. So when an electrical conductor cuts through magnetic field lines, we then say a potential difference is induced. Now, potential difference we know to be the source of energy in an electric circuit, normally provided by a battery. And this word induced is really important because it's electromagnetic induction. It's induced potential. Induced means to bring about. So don't miss out this word, right? A potential difference is induced. Then, if the circuit is complete, a current is also induced. So this is how we're generating electrical current. We're getting an electrical conductor, we're cutting magnetic field lines with it, which induces a potential difference across the ends of the electrical conductor. And then if there's a complete circuit, a current is induced, right? Now, the thing they added on to GCSE when they updated the spec that's a bit tricky is this induced current, something a bit more about it, right? And this induced current also creates a magnetic field. You remember earlier on in magnetism, you've learnt that like when we have an electrical conductor, we use this right hand grip rule, and an electrical conductor also has a magnetic field around it, right? So when there's a current passing through it. So if we're kind of like creating a magnetic field, using a magnetic field to create a current, we're also going to be creating a magnetic field, because whenever we have a current, we have a magnetic field. And then there's a kind of potential, I suppose. The main way that I think of understanding this law is that if this magnetic field kind of like is attracted to the one that it's in, you could get this thing suddenly like moving, almost like moving for free, because you've created you've moved it through a magnetic field, and then it's suddenly becoming attracted. It's going to start to accelerate. It doesn't make any sense, but that would violate conservation of energy. So this magnetic field created always opposes the change that causes it, which means if you're trying to like turn a generator to generate electricity, it's actually harder than you'd expect, because you're getting this kind of like magnetic repulsion happening to kind of prevent you from generating electricity. Lenz's law, it's called Lenz's law, which is what we kind of explicitly called it at A-level. But at GCSE, really just this idea that this magnetic field opposes the change causing it makes it slightly harder to turn generators is all that's necessary. Now, this is called the generator effect because it's generating electricity, or electromagnetic induction because we're inducing things using electricity, inducing electricity using magnetism, electromagnetic induction, or induced potential, because this is just 3 ways of saying the same thing. The effect at GCSE is the generator effect, right? So if they say what effect is this an example of, it's the generator effect, as opposed to the motor effect, which is when you're making things move using magnetism. How can we make this generator effect greater? I mean, this is electricity we're talking about. This is such a game changer, being able to power things, and you know, like whatever you're watching this on, that's electricity. So this is a big deal. How can we increase this? Well, essentially it's about making sure we're cutting more of those field lines every second, so we can turn our thing faster, move our thing faster. If we've got a coil of wire, we can like double up the numbers of coils on it, or we can do a stronger magnetic field. Now, B is the symbol for magnetic field, and actually it's called magnetic flux density, and that's how we measure the strength of a magnetic field, with the magnetic flux density, and it's measured in Teslas. Often forgotten. So you know, you need to remember this. You don't need to worry about remembering it for rote. You need to remember that it exists, but you can always look on the equation sheet, because the equation F is BIL is given for the motor effect, and that has magnetic flux density as B. They don't tell you it's in Teslas. You need to remember that. Now, if we want to reverse the direction of the induced PD, we're going to reverse the direction of motion. So if we move it one way through the field, it'll produce PD one way. If we move it the other way, back again, it'll produce PD the other way. Now, the two uses for this are generating electricity through an alternator or a dynamo. Now, the biggest difference between them is that an alternator allows us to produce alternating current. It's kind of like what we're naturally going to produce, actually. The dynamo has a few extra tricks that allow us to produce direct current, which is what produces in a cell. Now, the alternating current produced like from this, and the direct current from produced like this. So alternating current will look like this. It'll go up and down like that. Sinusoidal. If that's a word that makes sense to you. And the direct current, it actually just looks like this. So it kind of bounces up and down. Now, this is one complete rotation here. This bit here, that would be one complete rotation. This is one complete rotation there. So if it says two rotations, it's two basically like sine waves. And here it's two kind of like bumpy bits. This is direct current. It does stop to zero, but it's all in one direction. None of it goes in the opposite direction. So that's why it's direct current. Now, alternators and dynamos, the key thing is that you are turning them, right? Or whoever is doing the experiment, or whatever is turning it, you're turning it, right? And turning a turbine is a really easy way to turn kinetic energy. It's a really cheap and easy way to generate electricity. You can generate electricity just by moving a wire through a magnetic field, but this turning motion is really easy to create through falling water or steam or whatever it is. So it's just how we generate electricity. It's not necessarily like the only way, it's the way we do it. So it's what you learn about. Now, then there are two little bits here. So both of these, right, have brushes and some sort of like brush-like connection here. And that basically stops the wires from getting tangled up. You can't have like a complete connection to this, otherwise you quite quickly get your wires all tangled up as you turn the coil. So normally there's brushes. I mean, sometimes the simpler thing to do is to turn the magnet, but this is the case of turning the coil. Now, this has a slip ring, right? So it's called a slip ring, which just basically means the brushes slip over the two connections, and that's what produces you the alternating current. The dynamo, however, has a split ring, right? It's called a split ring commutator. And this is what makes the difference between the alternator and the dynamo. The split ring commutator reverses the directions every half turn. So instead of this bit going down there, you reverse the connections, and so it keeps going in the same direction, right? That's what it does. It reverses the direction every half turn, right? And that's what the split ring commutator does. Now, don't get confused between dynamos, alternators, and motors. A dynamo and alternator U-turn, and often they have an ammeter, right? If it was a motor, you'd have a battery and it would be turning by itself. The biggest mistake I see people make on these exam papers is they just see something, they start describing a motor, but you can't get marks for here. This is an alternator, doesn't have a battery. You are moving it, and you are inducing a potential difference when you cut through the field lines. And then if the circuit is complete, a current is induced. Now, I've got a model of this, right, slightly upgraded from the one I made last time. This is my uniform magnetic field. So here there would be a north-south magnet, and here there would also be a north-south magnet. And then these are just the bits in between the two magnets that show the magnetic field. Now, these yellow lines represent magnetic field lines. You can't actually see them. They're not visible, but they are there. And when we generate electrical current, the reason why we generate current is when a wire, so if this was my wire, cuts through these field lines, it generates an EMF. right? Or sorry, it generates a potential difference. Now, it does that whether or not it's connected into a complete circuit. However, you only get the current if it's connected into a complete circuit. So you can see that if I take my coil of wire like this and I rotate it in the magnetic field, I mean, I can't do that because I've put physical wires, but when I try and rotate this, I would in theory be cutting through these field lines, and that is what generates the potential difference, induces the potential difference, and then causes the current to flow if this is complete. Yeah. So when you think about all these, field lines and everything, it's hard. It's really hard. Often the difficulty as well is you've got like this crummy 2D diagram trying to show something happening in 3D because it has to be in 3D here. But the idea is if I move my coil of wire like that, I'm not cutting through field lines. If I go like this, I'm not cutting through field lines. It's only if I try and move it sort of down through here or rotate it in here that I'm going to cut through field lines, that I'm going to get that potential difference induced. Right? So it is difficult, this topic, because you are trying to visualize something in 3D, and they often give you, like, I feel like, not entirely helpful 2D diagrams. Right, so that's the end of the GCSE part. I've realized this is 10 minutes, so I'm going to stop this video and upload it separately, and then I'm going to do the A-level one, which will carry completely on from that. But otherwise, like, nobody wants a 20-minute YouTube video. It'll take ages to upload.